Hello and welcome back. Last time we saw how to use the pH log formula to work out the concentration and also the pH level of acids and water and some mixtures of both. We did that for part A and B. Now we're looking at question C. I'll just scroll down a little bit here so we've got a bit more room. A solution is made by diluting 100 milliliters of an acid. So we've got a capacity there. We know it's an acid and we've got a pH of 1.3 with water. We've got some water. Excellent. If the solution has a pH of 2.5, that's another key piece of information. How much water, was added? So we're looking for water. How much water was added? Well, let's write that key information down. So question C. We've got an acid. We have 100 milliliters of that. Oh, that's an M there. That's the same as 0.1 liters. Since our concentration is given in liters, over here, everything we want it to be is per liters. It's very important, so just keep that in mind as we continue working. Keep everything in liters if possible. We've got an acid, 0.1 liters, and the pH is 1.3. We also have water. This water, though, is unknown. It says how much water. So we have X liters of water, and we know the pH of that water is just 7. We want to find how much water there is. So if we scroll down a bit, so we've got some space. Here we go. We know that the acid plus the water will give us a solution. And we know the pH of this solution. The pH is 2.5. Let's just double check that. Let's look back up at the question. pH 2.5, fantastic for question C. So before we had acid plus water equals solution as well in question B. So let's try that same technique here. Now if you've been paying attention, you'll realize that this pH level directly relates to the power for the hydronium ions. So the concentration of hydronium ions for this acid would be 10 to the negative 1.3 moles per liter. And we can do the same for this pH of 7. We've done that calculation question A. So we know this. We know about the concentration of hydronium ions per liter. The thing is, our acid is only 0.1 liters and our water is X liters. So to work out the total number of hydronium ions in the acid, we would do 0.1 times 10 to the negative 1.3. That would represent the total amount of hydronium ions in the acid. Next up, we've got water, and we don't know the amount of water we have, so that's X multiplied by 10 to the negative 7. And that will equal our solution. Now, at this pH of 2.5, we know from previous examples that will lead us to a concentration of 10 to the negative 2.5 moles per liter. If you're not sure, please use the pH formula. pH equals negative log 10 H3O plus. So just sub in the pH of 1.37 or 2.5 and you'll get this value for the H3O plus, the hydronium. Now the solution, how much of the solution do we have? Well, we'll have that acid, of course, plus whatever amount of water that is. And we saw with the acid and the water, if we multiply the amount you have by the concentration, that'll tell you how many hydronium ions you should have. So this solution has a pH of 2.5, which means we would multiply that amount of water and acid by 10 to the negative 2.5. And this problem is just a pure algebra problem. Now this one might look a little bit complex, but if I do a little example over here to the side, if I had, for example, 6 plus 3x equals, in brackets, 1 plus x times 2, you might think, oh, I know how to do this red bit over here quite easily. And the same idea would apply over here with our problem. So you might think, first up, I want to expand this bracket over here. You're absolutely correct. So we'll do that first. 0.1 times 10 to the negative 2.5 plus x times 10 to the negative 2.5. Be really careful with your powers here and all of these ones and zeros that you don't drop anything as you work through. On the left hand side we've got 0.1 times 10 to the negative 1.3 plus x times 10 to the negative 7. So I'll just continue my easier example over on the right here. If I expand this, I'll get 6 plus 3x equals 2 plus 2x. Next you might go, oh, well, I want to get all my x's on one side and all my constants on another side. So I'll move all the x's maybe to the right hand side, all the constants to the left. So I'll have 6 minus 2 equals 2x minus 3x. And we want to do the same with our real example here. Let's get all of these x's across. So this here, that's a single term of x, and this here is a single term of x. Let's get them to the right hand side, and the constants will just shift to the left with a bit of algebraic rearranging. So 0.1 times 10 to the negative 1.3 minus 0.1 times 10 to the negative 2.5. That will equal x times 10 to the negative 2.5 minus x times 10 to the negative 7. Next up, now here we could add these together, but that would be a little bit messy. Instead, on the right hand side, just here, we can see we've got a common factor of x. So we can take that out the front. X. And on the inside of the brackets, we'll have 10 to the negative 2.5 minus 10 to the negative 7. On the left hand side here, that's just a number, but I'll just leave it in its exact form. And now you can see we're one step away from getting x by itself. X will equal 0.1 times 10 to the negative 1.3. See, I said to be careful with all the negatives and zeros and ones. That's a 0 there, by the way. Let me just make that a bit clearer. Minus 0.1 times 10 to the negative 2.5 all over 10 to the negative 2.5 minus 10 to the negative 7. And if you do all that, you plug that into your calculator. What do you get? Let me plug it into my calculator. I'm going to get 1.485, etc. And that would mean that we would need 1.485 liters of water to get that pH of 2.5. What a fun question. This one, we really didn't need to apply any log laws, except for, I guess, working at the concentration up here. But if you've been following along, you'll notice a pattern, and the concentration directly relates to the pH. So let's look at question D now. Question D, let's scroll up. A solution is made by mixing 500 milliliters of acid. So we got 500 mils of an acid. It's got a pH of 2.5. And this time, we're mixing it with another acid. Ooh. With 400 mils of an acid of pH 3. What is the pH of the solution? Wow. Alrighty, we got two bits of information just like before. We have two things. We have got an acid and another acid with different pHs and different amounts. So let's write that down. We've underlined it, but let's write it down so it's a bit clearer for us. So this is question D. We've got acid 1. There's 500 milliliters of that, or 0.5 liters. This one has a pH of 2.5. Now we know that is just the concentration of 10 to the negative 2.5 for the H3O plus, the hydronium. we've also got an acid 2. This one we only have 400 milliliters of, that's 0.4 liters. That's got a pH of 3, and that concentration is just 10 to the negative 3 for the H3O+. We want to find out the pH of our final solution. So just like before, if we think about it, it's acid 1 plus acid 2, that's going to equal our solution. So acid 1, we've got to do 0.5 times 10 to the negative 2.5 plus 0.4 times 10 to the negative 10 to the negative 3. And that will equal our solution concentration. But you got to be careful here because the solution concentration only represents 900 mils of solution, not a full liter, and our concentration is always per liter. So our solution pH, let's just call it pH. It's the unknown pH, so we can work it out doing this. And if we just put this into our calculator, oh sorry, it won't be pH, silly me. It's going to be our H3O+, that's the concentration, because we're using our 10 to the negative 2.5, which is our concentration of the acid 1, and 10 to the negative 3, which is concentration of acid 2. So if we put this into the calculator, oh sorry, we want to get H3O+ on its own first of all. I'm jumping the gun. Very dangerous. 0.5 times 10 to the negative 2.5 plus 0.4 times 10 to the negative 3 all over 0.9. That will equal our H3O+. And put that into the calculator. What do we get? We'll get something very close to 2 point. Let me have a look here. 2.201 times 10 to the negative 3. And that's our concentration of H3O+, but we want our pH. Remember our pH formula? pH equals negative log 10 H3O+. So we just sub our value in, this one down here, for our H3O+. So pH equals negative log 10 2.201 times 10 to the negative 3. And if we put that into our calculator, we get pH is equal to 2.657. And let's just check we've answered question D. It wants the pH of the solution. We've worked that out. There it is, 2.657. Alrighty, that's it for today. This was a really fun question. When I first looked at it, I had no idea how to do it, but just using the information provided, I was able to work it out. If you're able to just write down the information given, for example, this bit up here, I think that'll really help you out because you'll see what you've got and it might just lead you down the right path. Anyway, that's it for today. Thanks for joining me, and I'll see you next time.